With this video, I'm going to explain what ions are. So when we talk about elements, we know that elements have three subatomic particles. They have electrons, protons, and neutrons. Those protons and neutrons are found in the center of the atom at the nucleus, and the electrons live and run around in a cloud outside of the nucleus. So sometimes you can have enough energy come in and eject an electron out from the atom. And when that happens, that forms an ion. So now there is not an equal number of protons and electrons in the atom, and so the atom takes on a charge. Other times, electrons could be added to the atom, which would increase the number of negative charges that atom carries and make it be a negatively charged ion. So negative charged ions, which usually we just depict it with a negative circle, those are called anions. And positively charged ions, we call them cations. How do you remember what's what? Well, I just remember there's this super cute little cat. Makes a cation. All right, so cations mean, right, so if you have an overall net positive charge, so protons are positively charged, neutrons are neutral, and electrons carry a negative charge. So if you're overall positive, that means you're electron deficient. And if you have an if you have an overall negative charge and you're an anion, that means you're electron rich. Okay. Usually we don't talk about the difference in protons because if you change the number of protons, you change the element, right? Carbon always has 6 protons, period. If you removed a proton, you would not be carbon anymore. You would be boron. But you can add and remove electrons in that outer shell, and usually there's a trend when you look to see how electrons are added or taken away from elements when we look at the periodic table. So here's our periodic table of elements, and way over here on the far right, these are our noble gases in group 8. Noble gases are the most stable, and that is because, except for helium, their outer valence electrons have a full octet. So it is super duper happy. There are 8 electrons in that outermost electron cloud. If you were to move in one to group 7, those elements only have 7 valence electrons in their outermost electron shell. To be a little more stable, all they need was 1 more electron. So what you end up seeing is that the halogens, group 7, usually take on 1 additional electron and become overall negatively charged, and then that mimics, their outer electron shell mimics that of noble gases. Remember, noble gases are super duper stable. They don't react with anything. If you tell a noble gas a joke, it's not going to react. Okay, oxygen. So if we move to the left one, then we gain 1 electron, so we look like we have noble gas configuration. What about oxygen, which is in group 6? Oxygen has 6 electrons in its outer electron layer, its valence layer. And so if you added 2 more to that, 1, 2, you would have an outer valence shell that had the full octet. So oxygen, usually you see that as O2 minus. Same thing with sulfur. Sulfur tends to be a 2 minus, and selenium tends to be 2 minus. If you add 2 electrons to the outer shell of sulfur, it has the electron configuration of that similar to argon, right? Selenium would look similar to krypton, and oxygen would look like neon. Nitrogen and phosphorus are really the last 2, and potentially arsenic. But those 3 elements, if you added 1, 2, 3 electrons, they would also have an outer valence shell that mimicked that of a noble gas with a full octet. Carbon we don't really see carbon as 4. Okay. Then we move here to group 3 elements. So we have been adding electrons, right, to these outer valence layers to get to noble gas configuration. But notice that actually when we hit group 3, it's positively charged. So it's a cation, which means that it is electron deficient. It doesn't have the correct number of electrons in its valence shell. In fact, it's missing 3. So if you miss 3, so when you add electrons, you can move right on the periodic table, and when you remove electrons, you can move left. So if you were to lose 3 electrons, let's see, if you lost 1, you'd kind of look like magnesium with your valence electrons. If you lost a second one, you'd look like sodium. And then if you lost a third one, oh look, you would look like neon. So notice that those electrons can be removed from aluminum's outer valence shell, 3 of them specifically, so that it can have the noble gas configuration of neon. Group 2 elements are always going to lose 2. Okay? So they'll always lose 2 electrons, and group 1 elements will always lose 1 electron. And again, that's because if you're a sodium molecule and you lose 1 electron, you would go to the left, but that table wraps around so you look like neon. If you're cesium and you lose 1 electron, you go to the left and you would look like xenon. If you're calcium and you lose 2 electrons, 1, come back, 2, you would look like argon. So whenever you look at the periodic table and you want to create ions, disregard this middle area. This is Dr. Knapp's favorite area. That's inorganic chemistry, and the rules there are slightly different, and we won't really get into them. But I will require you to know the rules for group 1, group 2, group 3, group 5, 6, 7. Okay, so usually it's only going to be add or take away 3. So back, I guess, to an example of aluminum. Why is an aluminum -5? Well, every time you would to add an additional electron, that takes a lot of energy. So you could add 5 electrons and look like argon, or you could take away 3 electrons and look like neon. Taking 3 away is going to require less energy than adding 5 electrons. Okay, so that's where it's kind of like this group 4 is the tipping point. So if you're to the right of that, you're going to be adding electrons, and if you're to the left of that, you're going to be removing electrons. So you see a lot of anions and you see a lot of cations. When we name these compounds, if you're cationic, you just keep that middle name. So this is lithium, sodium, magnesium, calcium, potassium, rubidium. This is aluminum. However, if you're an anion and you gain electrons, your name changes just a little bit. So these are, again, the halogens. So this is fluorine, chlorine, bromine, iodine. And this is oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, right? So those are those. What you should do is you'll take the ending, remove the ending. So fluorine, take off INE, and you instead, in place, you add IDE, ide, fluoride, chloride, bromide, oxide, sulfide, nitride, phosphide. Those are the typical ones. You know, even down here, this you don't really see that a lot. So that's when we name compounds, and we'll always name things cation then anion. So if you wanted to, lithium fluoride, right? Not lithium fluorine, it's lithium fluoride, sodium chloride, aluminum chloride, aluminum bromide, calcium iodide. So you see how we always are going to name the cation first, the anion second. Lastly, when we are going to make molecules, we have to make sure that they have a net neutral charge. What I mean by that is, so lithium carries a +1 charge. So if you wanted to pair up lithium with fluorine that carries a -1 charge, you could do that at a 1-to-1 ratio. Because for every 1 positive charge, there's 1 negative charge, so that evens out to be net neutral. If you wanted to add lithium to oxygen and make lithium oxide, oxygen has a -2 charge and lithium has a +1 charge. Therefore, you would have to double the amount of lithium right? So then you'd have 2 positive charges to counter these 2 negative charges. So you would call it lithium oxide, and it would have the molecular formula of LiO. But remember, we had to double the amount of lithium, so you would say it's Li2O. Now, you would not call this dilithium oxide, and that's the beauty of naming ionic compounds. We scientists know that lithium in an ionic compound will always be +1, always, always, always. We know that oxygen will always be 2-, always, always, always. It'll never be -5 or -10 or anything crazy like that. You know, these are good rules and set in stone for turning elements into ions. And again, ions are changing the number of electrons. Now your book has some common polyatomic ions. Polyatomic, don't freak out, that just means it has more than one atom, right? Many atoms, and that are really common. And some examples are the hydroxide, which is OH-. We have our acetate ion, which is C2H3O2-, carries a -1 charge. We have our carbonate, CO3 2-. Each one of those CO3s carries a 2- charge. And we have a nitrate, NO3-, and then we have a sulfate ion, SO4 2-. So those I'm not going to ask you to memorize, but you can always look at that table. It's page 118. There's a few more you will be asked to work on in some of the problems. But let's work a few problems. So if we needed to write and name the chemical formulas for the following combinations, the first one would be sodium and sulfate. Now remember, when we're going to, so actually I just named it, because again, the beauty of naming ionic compounds is you just state what the ion names are. So that's sodium sulfate. But how do I write that chemical equation, keeping in mind that I need to make sure that my net charge is 0. Notice that sulfate has a -2 charge and sodium only has a +1 charge. Therefore, I'm going to need 2 atoms of sodium for every 1 sulfate ion to counterbalance it out so that I have a net charge of 0. So how would that look if we wrote it? You could write it maybe one of 2 ways, Na2SO4. That would be one way to write sodium sulfate. And the other way, just in case you wanted some clarity, you could add the parentheses around the polyatomic ion to know, especially for beginners, that all that stays together as 1 unit. So you wouldn't break that apart for any reason. In another example, we can look at how would you combine aluminum and oxygen to form an ionic compound. You'd probably need to run back up to or look at a periodic table to find aluminum, which is here. So aluminum is always going to be +3, and oxygen, which is group 6, and it's always going to be -2. Once we remember or know that information, so aluminum's +3, oxygen's going to be -2, we need to make sure that overall the ionic compound is net neutral. So if I right now I just mixed it 1-to-1 the way it is for aluminum oxide, that would have a net positive charge, right? +1. +3 -2 is +1. So I need to balance this. And one of the easiest ways to balance it is find the least common denominator between the two. I'm pulling up old math things from back in the day in high school. What is the least common denominator between 3 and 2? Sometimes you just multiply the things together and that's it. 6. Yeah, so 6 ends up being the least common denominator. So if I had a +6 and a -6 here, when I added those two numbers together, I'll have net 0, right? So how many aluminums do I need in order to get a +6 overall charge? I'll need 2. How many oxygens will I need so that I have an overall -6 charge? I'll need 3. So when I write out my molecular formula for aluminum oxide, it's Al2O3. All right, last, name the following compounds. So this is a little easy, and this is where we just look at the formulas and we just kind of say what they are. And knowing what the names of the polyatomic ions is going to be incredibly helpful here too. So for the very first example, I have potassium, and then this, it's not potassium nitrogen oxide. No. That NO3 is actually one of the polyatomic ions. So again, that's why having this table 4.3 right in front of you will be helpful. So that's potassium nitrate. And what about this next guy? So notice I have something in parentheses here, and this is another one of those polyatomic ions. This is ammonium. So this and this SO4, that's not ammonium sulfur oxide. No. SO4 is another polyatomic ion that should always be kind of grouped together as one. And so that's a sulfate. So this is ammonium sulfate. What about this example here? This is not iron sulfur oxide. No. This is iron sulfate. Remember, and when you see SO4 grouped together like that, that is the sulfate ion. In the last example here, I've got my magnesium phosphate. Okay, so practice naming and writing chemical formulas for ionic compounds. You'll have plenty of practice in your book and on the homework.